Good afternoon to all the attendees and good afternoon to our jury. My name is Ahmed Hadi, and today I'm going to present to you an idea that will revolutionize the health sector, Wi-Fi, an AI-based and secure health monitoring system. We take you through the journey that stemmed within the problems of the ICU. It starts with the patients that would be admissioned on a regular basis that would be burdened by the amount of wires and sensors that is attached to their body, causing them a huge deal of burden. They're not able to lay down or even move in a natural way, and any subtle movement will cause one of these sensors to be detached, now causing another set of problems for the health medical providers, such as the doctors and nurses, that would have to deal with regular false alarms and alarm fatigue about these inaccurate readings that will later on cause major catastrophes for those patients. And to even look outside of the ICU, we have problems in the cases of those with chronic diseases or elderly, or even in the case of pandemic, those individuals are not able to go to the physical centers to receive the needed treatment. We even can look to infants who just got born and they're the most sensitive time of their life. They need to be the close to their mother as possible, and they have to be put in an incubator with all these sensors attached to them. Now, all these catastrophes will lead to main problems globally. 70 million deaths are attributed to heart attacks, and even when we look to the UAE alone, 30% of the UAE citizens also die from heart attacks that are not attended to in time due to the limitations of these traditional equipment. Now, to address this, we needed to find a solution, and the main cause of all these problems are those sensors or wires. We decided to completely remove them and replace them with Wi-Fi signals. Now, the monitoring of vital signs will be done through two routers on either side of the patient that will extract CSI data and be sent to a server where we're going to have our AI model process those data and then predict both the heart rate and respiration rate. But let's go back a step and start from the beginning, get our story, and how we even got introduced to CSI data. It's through our extensive literature review that got us a lot of ideas on what we can do in order to replace sensors and wires. And what is CSI data? CSI data is basically the data collected by any router that would enable you to describe the movement that would happen in a single room. It can detect micro movements such as somebody falling or even walking, and even very subtle movements such as the chest movement of a certain patient as they're breathing. Looking into CSI, we also did a long requirement gathering to understand all the other problems other than monitoring the vital signs. What does hospitals need in today's world? And we've done over 500 responses to the public community and 200 more responses along with multiple interviews to healthcare providers in order to understand that not only we have the problems of the wires and sensors, but we need a contactless system that will integrate AI algorithms that are currently absent in the healthcare sector and enhance patient comfort. And all that will be processed through an architecture of a presentation tier for the web dashboard and mobile application, a data tier to save all the data, and finally application tier that'll be in charge of data processing, deep learning, and heart rate and breathing estimation. So let's go and explore our application tier, starting with the breathing rate estimation. It all starts with 500 packets being collected every single minute, and then they will be gone through our server where we start the filtering process. It will go through simple moving average and Happel filters in order to remove any outliers, and then we'll go through a sophisticated delay filter in order to smoothen the data. Whatever the result will be later on presented in the healthcare provider's web dashboard in real time. Now, simultaneously, every single minute, 60 packets will be taken into a separate list and will be thrown into another wave of sophisticated delay filter in order to smoothen those data even more, and will mimic some similar to how the wavelength or respiration rate is shown in the ICU monitors today. And the result was shown here, where we have a graph of the respiration rate of the patient, as well as in order to estimate the breathing for the patient, we're going to start to calculate the peaks. The peaks over here will indicate how many times the patient has to actually breathe per minute, and that will be put into the healthcare provider's dashboard in real time. Now going into our heart rate algorithm, that's where the AI implementation starts. And our journey started looking into what kind of data set we want to have. We've looked at a lot of public data sets, and we found one from a public paper with the name eHealth. It had a lot of diverse information, 118 participants that included both the CSI value data as well as their heart rate monitor from a Samsung watch. But what it's important to see that all the position or the participant got monitored from 17 positions. Those 17 positions actually divided into either static positions or moving positions. We excluded, for our objective into implementing this in the ICU, we excluded any of the moving positions, focused only on the static positions, specifically when the patient is sleeping. But we faced a problem, as the data set initially was imbalanced. Now, to solve this, we opted for data augmentation, where we take in some of the static positions, which were sitting positions, and took them as variations of the readings in order to balance out the data set. But that was only in the training phase. As in the validation stage, we ensured that we're only going to validate on sleeping positions to ensure the accurate results. As all other distributions, we had 88 male to 30 male participants in the data set, and we had multiple diverse information from height, weight, BMI, and age. Now with that done, we can start our AI implementation. And there's something that's very unique about the data set that we have, unlike other public data sets we have found, is that one has raw CSI data. Other data sets were already processed, but this gives us the opportunity to create our own processing phase. And we all start by collecting 500 packets per minute. Those packets are composed of 256 subcarriers. But to ensure effectiveness, we only selected the top 16 subcarriers, and we calculated that based on their variance. Meaning those subcarriers with the highest variance, they're the ones that have the most movement, indicating things such as chest movement of the patient. We then move on into what are the data in CSI. CSI is made up of two basic values, amplitude and phase. Amplitude is the strength of the signal, and phase refers to this phase delay or the signal delay. And we take that, we split them in two in order to start processing them. We start with amplitude. Here. We process the amplitude by oscillating the vital signs frequency. Usually either heart rate or even breathing rate, their frequency is between 0.5 to 3.5 hertz. And we ensure to isolate only that frequency from and exclude all the other frequencies. Then we take that frequency into a Happel filter in order to remove any outliers or noise that would be positioned within that frequency. And with that, amplitude is now processed and ready. As for phase, we've taken it first into Happel filter, remove any outliers or noise, and then to a Butterworth filter in order to smoothen the signal, and then finally another phase of Happel filter in order for further re-enhancements in any outliers that were not caught on prior to the smoothing. We calculate both the phase and amplitude, and we can just understand to it based for our AI modeling input. We start here with a 3D matrix that would contain all our values, the 500 packets we've collected, the 16 subcarriers, and the received 2 values after being processed, which is phase and amplitude. Once that's ready, we're going to convert that 3D matrix into a 4D tensor, dimensional tensor. That additional dimension is for our batch size that will contain all of our CSI records. Once the input layer is ready, we can take it into our CNN model, which is composed of 3 shared layers. Starting with the convolution layer, that is responsible for feature extraction from the input data by using a lot of filters and convolutional operations, which will result in a feature map that would have all of the detected patterns for the patient chest movement. It will go into a batch normalization layer afterwards, which will normalize the data and stabilize it and ensure that the batch distribution is always consistent, which will prevent overfitting and improve our training process. Ending with a max pooling layer, which will downsample the data and ensure it only will focus on the most prominent features by checking some of the important features such as the highest value. It will ensure that only the important features remain. It will focus on that and reduce the size of the data in the process. We end with a flatten layer where the entire 3D dimension will be converted to a 1D vector and then fed into our fully connected layer. That dense layer is responsible for checking the correlations between the classes and our features in order to check or make decisions based on interpreting those features from the feature map. We need to take an important note about how our AI hyperparameters, our process was run in maximum of 100 epochs with a batch of 32, and we have early stopping to prevent any overfitting, ensuring that if we've reached 20 epochs without any improvement, then the entire process will stop and we're going to return the lowest MAE. And for evaluation metric, we're using a mean absolute error. For our results, we used a 70-30 split, and we got a high absolute mean error of 5 to 6 ppm, and we also followed with a 10 cross validation that improved MIE of 8 ppm in heart rate estimation. To understand how we've reached our process, we can see how we compare to all the other papers that we've checked into, and we've seen that we got the highest, or even the lowest in this case, MAE compared to all the papers that we've read. We also bought one of the most highest used devices today, the Whoop Watch, in order to check our data and compare to the AI results in real time. And we got such high promising results in multiple positions and for more than one participant, getting that promising results that we are able to detect heart rate accurately. And that would be the end. Thank you so much.